working at low temperatures, where actually these processes tend to be much more pronounced, and in general, they're used for a kind of a different class of problem, in particular things like figuring out how cold the ice ages were, for instance, is a big focus of isotope geochemistry. So until quite recently, actually, the general assumption would have been that at the sorts of temperatures where you are in the mantle, or especially the lower mantle, core mantle boundary, these isotope separation processes are so trivial that we might not even worry about studying them, that the temperatures are so high that things are disordered, at least isotopes are disordered, because the driving energies tend to be so small. But over the last few years, in part because of technological developments in the measurement of isotopes, we've been able to detect things that we couldn't detect before. So we actually do see heterogeneity, resolvable heterogeneity in planetary scale systems and high temperature systems, and by extension, perhaps in high pressure systems. And there is kind of a little community, a nucleus of a community of people who are worrying about how those processes might come about. And so I'm the one in this group maybe who does kind of density functional theory type stuff, but that's actually not the only way that this has been addressed. So Jem Rustad, who some of you may be familiar with at UC Davis, has published actually a little bit on high pressure iron isotope separation processes using molecular cluster kind of models, where he's actually making not exactly a unit cell, but some discrete atomic cluster approximating the structure of an iron oxide or iron silicate mineral, and then imposing a boundary condition that approximates the pressure that he's interested in and calculates thermodynamics that way, so using something like Gaussian. And then Viniamin Polyakov has been working on pressure and temperature for isotope effects for decades. And he actually uses thermodynamic data, high pressure, high temperature spectroscopy, and sort of inverts that discretely, analytically, to get at the properties he's interested in. So there are actually many ways to skin a cat, which is kind of interesting for this problem. Okay, so rather than try to talk about everything I do, I thought I would focus on kind of one of the more high pressure oriented things I do, and maybe use that as an avatar for the broader class of problems that we're interested in. So I'll kind of focus in on one thing, but that's not the whole story. Okay, so to first order, the kind of sort of motivation for this sort of work is figures like this. This is from a paper by Bastian Georg that came out 3 years ago. These are, what's shown here is just a histogram of silicon isotope measurements. So this x-axis is the silicon 30 to silicon 28 ratio. Those are stable isotopes of silicon in various samples from the Earth, from Mars, from various classes of meteorites, and from the moon. And what's happened in the past 10 years is there have been some developments in mass spectrometry that allow us, at least in some nominal way, to resolve variations in these isotope ratios to the tune of 50 parts per million, 0.05 per mil or less. And if you look at these different classes of samples, you actually see that there's some evidence of perhaps heterogeneity, that the Earth and the moon, for instance, on this scale, are a bit more enriched in silicon 30 than Mars and the meteorites. And so one big motivator is, what is this telling us? We can measure this stuff. We don't exactly know why we're measuring it. So is there some useful information that we can extract from this, or vice versa? Is there some fundamental property of the condensation or differentiation of planets that's giving us these kinds of signals? And it's not just for silicon, I should say. This has been definitely found for iron. There are actually every few months, there's a new element that seems to come out where people are talking about differences or similarities between different planetary scale bodies. So the basic question is, what causes these kinds of signatures? Is it something about planetary differentiation? If it is it telling us about elements that go into the core? Is it telling us about chemical heterogeneity in the mantle? Is it telling us about crust-mantle interactions? Or is it telling us something even farther back in time? Is it telling us about heterogeneity in the star stuff out of which we're made? Is it telling us about condensation and evaporation processes in the nebula before we even had planets, or during cataclysms like a moon-forming impact, for instance? Okay, so the contribution I'm trying to make is to figure out what kinds of chemical processes at a very simple fundamental level might cause these types of signatures, kind of hopefully pare down the parameter space that we have to worry about and try to test. And this is kind of a blue sky thing. We don't actually know how these processes work at high pressure and high temperatures. We're making a guess. And one guess we're making right off the bat is that we can treat this as an equilibrium problem to first order rather than a kinetic problem, not because we have any particular reason to think it's equilibrium relative to kinetics, but simply because kinetics are a little harder to deal with. So we're going to look for the keys under the lamppost, so to speak, where there's light. And the basic idea is this is very similar to any kind of chemical partitioning problem. We're writing out a chemical equation. In this case, it just involves swapping of isotopes between two different phases, like a metallic core and a typical silicate. And we're trying to find an equilibrium constant for that reaction using thermodynamics. The interesting thing about this particular kind of thermodynamics is that it's actually not, it's really focused on thermodynamics that is usually kind of an afterthought. And in particular, where isotope partitioning happens at equilibrium, and actually in many non-equilibrium processes, is in vibrational energy. That if you have like an SiO bond, you might have an equilibrium configuration of the bond that minimizes the potential energy, but because vibrations are quantized, you can never quite get to the bottom. And if you have a heavy isotope that's vibrating more slowly, you get a little closer to the bottom than if you have a light isotope that's vibrating a little faster, right? So there's a little difference in the bond strength for different isotopic forms of the same stuff. And that little difference depends somewhat on what substance you're talking about, metal versus silicate or different oxidation states of a given element. And in general, the heavy isotopes are going to want to go to the things where they minimize the energy the most. And the light isotopes are going to want to go to the things where it doesn't really matter whether it's a heavy or light isotope. The energy only goes up a little bit. Okay, so we're basically mostly interested in the vibrational part of the thermodynamics. For normal mineral physics kind of problems, you may do a correction, but here it's really the whole story to first order. Okay, and the reason that this is kind of a good candidate for first principles type work is that in general, we don't know enough about the vibrational thermodynamics of interesting things to make these calculations based on the data we have in hand. Particularly for isotopically substituted forms of substances. These differences in frequencies can be very small. Even if you make a measurement, the resolution of a typical measurement isn't enough to say what you need to say. But it turns out that things like density functional theory can give you a very good picture of vibrational thermodynamics. So this is just a comparison of calculated and measured vibrational phonon frequencies for forced right from like Raman and infrared data. And there's a scale factor, which I'll come back to a little bit. This is with a generalized gradient approximation, PBE functional. We underestimate frequencies by something like 4% in this case. Okay, so to try to get at this particular silicon isotope problem, we started out with a really perhaps scandalously simple picture of the problem. We said, okay, we have two things that we have to worry about. We have to worry about the bulk silicate Earth and the Moon that we actually have samples of, which we're going to say is olivine, actually forced to write, not even olivine. And we have cores of things, which we're going to say, at least in the case of the Earth-Moon system, is iron silicide, this material payite. I'm sure I'm butchering the pronunciation, but there's a synthetic equivalent, Fe3Si. And the difference, of course, you know what the structure of a silicate is. Just we're making an assumption that the metal is something where silicon is bonded to iron rather than oxygen. And if we make a calculation of phonon frequencies and work out the thermodynamics based on how much that energy changes when you substitute one isotope for another one, you get a picture of something like this, where the green line is for forced right relative to this depiction of metal, and the little dotted line is pyroxene, polymerized silicate relative to the same metal. Doesn't seem to actually matter that much, which is good because we're assuming that the Earth is forced right, so it's nice to know that forced right's actually not that much different from pyroxene for this case. And the other really important thing we found that actually went into the first paper was that for this particular system, the chemical change from the perspective of silicon between silicate and a metal phase is so profound that even at temperatures of several thousand degrees Kelvin, there's actually a pretty big isotopic partitioning, with silicon-30 preferring to go into silicate rather than into the metal. And it turns out that this number of about 1.5 per mil is actually about what you need if you assume that about 5% silicon goes into the core. The Earth ends up, the bulk silicate Earth ends up in that case being about 0.2 per mil elevated relative to an undifferentiated body. So that worked out nicely. Okay, it doesn't really matter whether you look at pyroxene or forced right, actually zircon or quartz. They're all pretty much going to give you the same answer at this scale. Okay, but the big problem, of course, is that there's no pressure here. So this is a non-compressed result. in some sense. And we're assuming everything's harmonic, so temperature is being treated only in a very simplified way. And we know there's an important change in the chemistry of silicon in the Earth, that you have a change in coordination to things like perovskites, where there's six-fold coordination. But just starting from that simplified picture, there's likely to actually be a chance to cause these kinds of planetary scale signatures in stable isotope systems, even at high temperatures. This was subsequently tested using experiments. This is a sort of summary figure by a paper by Karen Ziegler and some other folks at UCLA and Carnegie, looking at the curve I just showed you as the dotted one here. This is an experiment done by Anat Shahar at 1 gigapascal. And these points over here are actually coexisting metal silicate pairs from some instantite chondrite meteorites. These are meteorites that are so oxygen depleted that in fact silicon dissolved into the metallic phase. So you can measure it, right? And it's not a perfect match, of course, but the general sense of things is actually pretty good. Okay, so this is low pressure, but we're interested actually in high pressure, and I'll get to that in a minute. But the basic point here is that in general, isotope geochemistry is not a high pressure science. For reasons I've already described, that usually when you're talking at high pressures, you're also talking about high temperatures where the assumption has been that these signatures are too small to measure. But also, there's a good reason why we usually don't care about pressure, and that is that substituting one isotope for another one is a trivial change in volume. So there's no PV work. So in terms of thermodynamics, first order, it doesn't matter what pressure you're at. There's an exception for hydrogen because hydrogen bonding is kind of this funny pressure-dependent thing in its own way. But the extent of consideration of this up until 5 years ago was only up to a few gigapascals. And here we're talking about pressures potentially that are on the order of the bulk modulus of the material we're interested in. So of course the chemistry is going to depend on the pressure once you get to that point. And in particular for this problem, it's important because one of the ideas for why the Earth is different than Mars, for instance, which also has a core, is that it's possible that the segregation of the core in the Earth occurred at relatively high pressures. This is kind of one of the ideas based on other metal concentrations in the residual bulk silicate Earth and our understanding from experiments of how metals partition between metal and silicate. One idea is that at the Earth, the core may have segregated at an some range of pressures, but effectively tens of gigapascals, where on Mars, maybe 1 gigapascal, and then of course the meteorites are talking essentially 1 atmosphere or less. And so on the Earth, we have to worry about the fact that over the pressure range of interest, the structure of silicates in particular is probably changing. And the metal's probably changing too, but actually we know so little about that, we're not even gonna make a first order cut at it. So what we really wanna know is not just what's happening with olivine Earth, but we also wanna know something about what's happening with perovskite Earth. And this is where my attempt to learn how to do quasi-harmonic equations of state and actually tie those to specific photon spectra that we can then do isotope substitution on came into play. And I think I've kind of got it, but I've made some simplifications, which I can show you later, but I'm afraid I'll get laughed out of the room if I show them right now. And actually, what you see when you try to put pressure into these pressure and temperature at the quasi-harmonic level is actually something kind of interesting for its boringness, which is that it doesn't actually matter very much. So we did a calculation with a ringwoodite structure, a pure ringwoodite structure, with 4 coordinated silicon, a calculation with perovskite at the core mantle boundary, pressure more or less. There's essentially no distinction between them. The models I showed you before would essentially overlap actually the red curve. They're a little bit above the ringwoodite curve. So the first order, incorporating pressure tells us that pressure doesn't matter, which is kind of weird. And we tried to do this a little bit more sophisticated way. This is stuff I've already told you. To actually maybe take account of the fact that this is probably a liquid process, not a solid phase process in the Earth's history. And so based on stuff like Stix-Rudikarki, where it was shown with more dynamical calculations that there appears to be a gradual transition with specific volume of the melt in its average silicon-oxygen coordination to try to incorporate in these models some flavor of that. And we did that essentially by taking our ringwoodite model and saying that's low pressure melt, and taking the perovskite model and saying that's high pressure melt, and then just mixing them according to the volume that we're interested in a particular pressure. So So we just essentially made a linear mixing model between those two things and said, melt